Today's probably going to be the shortest lecture of the quarter. And here's where we're at. We're just about done with separability, and we're going to start a new chapter next time. That chapter is going to be called Galois theory. So we're about to really start doing Galois theory. We've set the stage. We're ready to go. There's just one last thing, and if you remember a couple of lectures ago, I mentioned that it actually is it requires some hard work to produce a polynomial that's not separable. And last time we proved a theorem that characterizes what it means for a polynomial to be not separable. And so now what I'm going to do, and that's all we're going to do today, is we're going to identify a polynomial that's not separable. So this is just an example, right? A polynomial that is not separable. I mean, it's not that hard of work, but I mean, it's not completely obvious. So here's what we're going to do. So let's consider z2 parentheses x. Remember, this is the notation for the field of quotients of z2 bracket x. Right? So this is field of quotients of z2 bracket x, right? Z2 bracket x is an integral domain, which means there's a corresponding field of quotients. What do the elements here look like? They look like equivalence classes of polynomial over polynomial. Okay, and so here's where we want to work, and we'll say and let f be the polynomial. It's not an overly complicated polynomial. It's just t squared minus x. Here, this lives in, so we want to view this polynomial as living in z2 parentheses x bracket t. So these are polynomials with variable t, coefficients in z2 parentheses x. Okay, fine. So if sigma is the splitting field for f over z2 parentheses x, then what? And alpha in sigma is a root of f, then what? Well, okay, so that would mean, so plug alpha into f, what we get is alpha squared minus x equals 0, which means that x is equal to alpha squared. So now, f, that's equal to t squared minus x, which equals t squared minus alpha squared, which equals t squared minus 2t alpha plus alpha squared, right? We're in characteristic 2, and so plus and minus mean the same thing. And then this is equal to t minus alpha quantity squared. I guess, you know what, I could have done this, I don't know why I did this extra step. I could have written this, now that I think about it, t minus alpha, t plus alpha, and then remembered, oh, minus is the same as plus, so this is t minus alpha quantity squared. So either way gets the job done, but probably the thing I just realized is quicker. Anyways, so what do we have? We've got f f expressed in this way, which tells us that alpha is a multiple root. So it follows that alpha has a multiple root. Now, so letting G equal what? T. What do I want? Just T minus X. Yeah, T minus X. Right, living in Z2 parentheses X bracket T. We have that F equals G of T squared. So now if you think back to our theorem, so by theorem 4.10, to conclude that F is not separable, what remains is to show that F is actually irreducible. So we need to show that F is irreducible over Z2 parentheses X. Right? And if you remember, the starting of theorem 4.10 was to say that we have an irreducible polynomial, and then it's this if and only if statement that says that a polynomial is not separable if and only if you're working in a field of characteristic P, and that polynomial can be expressed as G of, I think I used X there, but X to the P, or in this case, T to the P. Right? So here P is equal to 2. Okay, so the goal now is to show that our polynomial is irreducible. If we can do that, then we can conclude that F is a non-separable polynomial. All right, so suppose that F is equal to, I know I used a G over here, but I'm going to read, this is a different G. Or whatever, I can't think of any other good letters. E, F, G, H, I, J. What's another good letter for a polynomial? G? There's no other ones. It's either F, G, and H. So, okay, I'm going to use G, H, where G is not that G over there. So suppose F is equal to G, H. For some G and H in K, not K, Z2 parentheses X bracket T, where the degrees of both G and H are strictly less than the degree of F. So that would be where the degree of G equals 1, which equals the degree of H. Right, so suppose that we have an honest factorization of F into smaller polynomials. Now, we just saw how this thing factors, right? So since sigma bracket T is a, I hope I used sigma T, or did I? No, I think I just wrote sigma before. Right, so since sigma bracket T is a UFD, what does that tell us then? Well, we already know how F factored, right? It factored as X minus alpha times X, or T minus alpha times T minus alpha. And so this tells us then that both G and H have to equal T minus alpha. So we have G equals T minus alpha, which equals H. And so what does that tell us then? So in particular, okay, these polynomials right here then have to live in Z2 parentheses X bracket T, which means that alpha lives in Z2 bracket X, or parentheses X. So in particular, alpha is an element of Z2 parentheses X. Okay, so what does that mean then? Well, it means that alpha can be expressed as a rational function, right? So let's let P and Q in Z2 bracket X, now bracket, not parentheses, be such that alpha equals P over Q, right? That's what elements of Z2 parentheses X look like. They look like polynomial over polynomial. All right, so then I'm just going to multiply over. So alpha Q equals P. And so I'm going to square both sides and then subtract the P squared over the other side. So alpha squared Q squared. Which order do I want it to be? Yeah, that's fine. Alpha squared Q squared minus P squared equals 0. But remember, alpha squared is equal to X. So it follows that X, Q squared minus P squared equals 0. And now we've got a problem. Because whatever P is, P squared has even degree. Same with Q. Q squared also has even degree. But then X times Q squared has odd degree, while P squared has even degree. So if you subtract odd degree minus even degree, you're not getting the 0 polynomial, right? So, so let's say which is impossible. Which is impossible. And the reason is that the degree of X Q squared is even, while the degree of P squared, oh no, I said that backwards, huh? Is odd up here, while the degree of P squared is even. All right, so what does that tell us? That tells us that F could not have factored in this way, which means that F is irreducible. So therefore, F is irreducible over Z2 parentheses X. And now we can just apply our theorem, so our conclusion is that F is not separable. Yeah, over whatever, over Z2 parentheses X. Okay, so that's it. We're done with the build up to Galois theory. Now we're going to start doing Galois theory. All right, so our next chapter. Yeah, anyways. All right, see you later.